Okay, this is the lecture video for MAC 1114, Trigonometry, and in this section we're going to be taking a look at angles and their measures. We're going to learn how to draw those angles based on a suggested type of rotation, either positive or negative. We are also going to learn how to convert between degrees and radians and vice versa. We are going to be using angles in certain application type problems like finding arc length, linear speed, and angular speed. Okay, so let's start off by learning how to draw the angles in a specific quadrant, whatever quadrant is suggested by the rotation. Okay, first you need to know how to spin in a positive direction and how to spin in a negative direction. Okay, first picture that you see here, and note that you are going to be concentrating on what are called angles in standard position, and I'll describe that to you through the use of these two pictures. Okay, an angle that's in standard position, and oftentimes we use Greek symbols whenever we are naming angles, although, you know, other things can be used to signify an angle, but this is just a very common convention. So an angle theta is said to be in standard position if its vertex is at the origin of a rectangular coordinate system. This is your rectangular coordinate system, also known as the XY plane. We have an angle whose vertex is at the origin, and the sides of the angle are called the initial side. The initial side always stays fixed upon the x-axis. It does not move. While the other side is what we call the rotating side, and that is known as the terminal side of the angle. This terminal side, it begins by being pasted to the x-axis as well, but it is the side that rotates while the other one always remains fixed to the x-axis. Okay, initial side stays fixed. Terminal side rotates to either quadrant 1, 2, 3, or 4, creating an angle between the two sides. So your job is going to be, to begin with, learning how to spin if you're being asked to represent a positive angle. Anytime the angle that you're representing is positive, you're going to let that terminal side rotate in a counterclockwise fashion. Okay, and as you can see, this is a picture of that kind of rotation. On the other hand, when the terminal or rotating side, as we call it, you can call it either thing, terminal or rotating side, when it spins in a clockwise fashion, then you're representing a negative angle. So rotating counterclockwise is for positive angles. You will drop down with your rotating side and spin in the opposite direction, which is a clockwise rotation whenever you're going to represent a negative angle. Okay. All right, so just the difference between how to represent a positive angle and a negative angle. As I stated earlier, that rotating side can either be in quadrant 1, 2, it can be in quadrant 4, it can even land on one of these axes. So we also want to be able to identify what quadrant the angle is that we created. So if you have to spin with your terminal side and that terminal side lies in quadrant 2, then this angle is said to be in quadrant 2. Notice that the kind of angle that you're seeing here, because you have a counterclockwise rotation, in other words, this terminal side, which began pasted to the x-axis as well, has rotated in a counterclockwise fashion, and therefore the angle that you're seeing here would have to be a positive angle. Okay, whereas this angle that was created by this terminal side rotating down to quadrant 4, that angle would be negative. because it is a clockwise rotation. Okay, this angle here, what's happened here is both sides of the angle were fixed upon the x-axis, but this one remained there, the initial side, while the other side rotated. This is the rotating side right here, the terminal side. This time the terminal side, instead of landing in a specific quadrant, it landed right on the negative y-axis. And anytime your rotating side lands on any axis, whether it be the positive x-axis, the positive y-axis, or the negative x-axis, or the negative y-axis, like what you're seeing here, it's been darkened in. So they're showing that the terminal side landed right there. Anytime terminal side lands on an axis, it's referred to as a quadrantal angle. Okay, then we come to learning various terminology that you may already be familiar with, but is something that is going to be used quite often, so let's review it. If your angle rotates an entire 360 degrees, as you can see in this picture right here in the bottom left-hand corner of the page, that is what we refer to as a full revolution, and you may know it as a 360 degree rotation, but that's equivalent to 2 pi. When you rotate half of a circle from there to there, that's 1 pi. As you can see in this picture right here, this is a picture of a 1 pi rotation. But when you rotate all the way and do the other half of the circle, then you have rotated to what's called 2 pi. And that's what we refer to as either a 360 degree rotation, but we can also call it a full revolution. Okay, in the second picture that you see there, the rotation has been 90 degrees. And you know that this symbol here, this little block, as a symbol that represents a right angle, but these are other ways that you can refer to it. If you know that 360 degrees is called a full revolution, then 90 degrees would be called a quarter revolution. Okay, you could also refer to this as a revolution of half a pi. Okay, because 1 pi is half a circle, but if you're only going to go a quarter of that, then you've gone half of a pi. Okay, last picture here, as I already stated, this is known as 1 pi. You could also talk about this as being equivalent to 180, because each half of a circle, every time you go half of a circle, you've gone 180 degrees, but that's also known as pi. And a third way to refer to it is as a half a revolution. Full revolution is all the way across, all the way around a circle. Okay, so just some common terminology that's used with respect to spinning around the circle. So in the very first problems that you are going to be doing in your homework, you're going to be practicing drawing certain angles, showing that you know which way to spin based on the positive or negative direction. Just look at, whether they're giving you a positive or negative, and knowing, showing that you understand where's 180, where's 360, what is half of that. And you should be able to represent these angles, whether they are given in degree form or in what's called radian form. When it's in pi form, that's called radian form. Anything that's equivalent to a decimal, and I think we all know once you get this far along in your math that pi is a decimal type number, and decimal type numbers are referred to as radians. So angles are given in either of those two forms, degree form, radian form. Okay, so if you're going to negative 90 degrees, don't forget all negative angles are represented in a drawing by rotating in a clockwise fashion. That's how you show that you're rotating in a negative direction. Okay, so and then you're also familiar with the fact that this is every quadrant's worth 90 degrees. Okay, it's just a quarter of revolution, 90 degrees. So you're going to show that you rotated this way by way of this arrow, and you're going to show where that terminal rotating side landed. Okay, so this would represent a rotation of negative 90 degrees. Okay, moving on to the next drawing. Draw the angle that represents pi over 2. Well, pi is the same thing as 180. 180 divided by 2, this is equivalent to 90 degrees. 180 divided by 2. Or you could just think of it, if you don't want to think of it in terms of degrees, just think of it as, okay, from here to here, half a circle would be 1 pi, half of that is up here. This is positive, and whenever it is a positive angle, as you're seeing here, you're going to rotate in a counterclockwise fashion. If I have enough room to write all this, counterclockwise. Okay, so I'm going to go like this. So I'm showing which direction I'm going in by way of my arrow on this arc right here. I'm showing where I'm landing right here, and I'm labeling it with the angle that I was presented, which was pi over 2, half a pi. Okay, in this next picture, this is what we're going to be working on the most, you being able to relate to fractional type angles. And I think the best way for you to think about this without going too crazy about thinking about fractions, although you're going to have a somewhat of a sense of where you're going, otherwise you won't know what quadrant to land in, and that's going to be super important. So we are going to solidify your understanding of fractions. So the best way is to think of the two most important landmarks, or two of them would be 1 pi and 2 pi. Now we're not going anywhere near 1 pi. In fact, we're going to stop before we even get to 1 pi by going to negative 3 pi over 4. And since we do have a negative angle here, we might as well say that we're going from here to here, in which case this would be called negative 1 pi. So I'm going to put a negative right there. And this negative 1 pi, I want you to think about the fact that the coefficient here is 1. It is negative, and that's because we're rotating clockwise. But instead of putting a 1 here, since this problem has to do with force, why don't we rename the number 1, which is the coefficient here, as 4 force? Because by understanding that the negative pi location is the same thing as negative 4 force pi, then you know that you're stopping before you get there, because you're only going 3 force in a negative direction. You're never quite making it there. So negative 3 fourths, because they're also going to want you not only to draw this and show that you understand the direction based on the negative, but also that you understand what quadrant are you landing in if you're going to negative 3 fourths pi. So here you'd be going negative 1 fourth, negative 2 fourths, negative 3 fourths. This would be 1 fourth, 2 fourths, 3 fourths. Okay, definitely before you get to 4 fourths. And then this would just be your rotating side. You're stopping right here. So you can show that you moved in a clockwise, you made a clockwise rotation because of the negative. And we're talking about your terminal side. Is the thing that's rotating. So as a clockwise rotation, this is the arm that rotated clockwise as signified by this little arrow right here. And then you're showing right at the end of that ray called the terminal side. This is your terminal side that you've rotated to negative 3 fourths pi. So that was before you made it all the way to negative 4 fourths. Okay, and that would be a picture of 3/4. 11/4 means that you are, you're going to continue rotating, but in force. Again, I would look at the denominator that they are bringing up in this particular problem, and I would label my landmarks based on that particular denominator. So again, you're rotating. This time we're rotating in a positive fashion. This is a positive angle. So we are going to do a counterclockwise rotation. So that's the way I'm going to be rotating with my terminal side. I want to be thinking in force. So this would be 1 pi. I'm going to be rotating this way this time because it's a positive angle. And instead of 1 pi, I'm going to call this 4/4 pi. That's the same thing as 1. The number 1 can be written as 3/3, 2/2, 4/4. Make it consistent with this denominator. Okay, so that would be 1 pi. By the time you come over here to 2 pi, that's the same thing as 8/4. Okay, this is 1 pi, 4/4, 8/4 is 2 pi. And by knowing those specific landmarks, you can make a very good estimate about where 11/4 is. Okay, so imagine that you started off with your initial side, which remains pasted to the x-axis and never moves. And then you have this one spinning side that goes to 4/4, 8/4, and then you have to go even further than that because you're going to 11/4. So if you're going to 11/4, that means you're going past the 4/4 mark. You're going past the 8/4 marks, and you're going 9, 10, 11. So 1/4 more, 2/4 more, 3/4 more. 11/4 is 3/4 beyond the 8/4 mark. So 1/4, 2/4, 3/4, you're right in here. And that would be 11/4 of a pi. And you can show that you rotated like this and then went beyond the 2 pi mark for an extra bit of rotation to give you that 11/4. In fact, we went exactly 3/4 more than this mark right here. And that represents you're going past 1 full revolution to get to 11/4. Okay, so 4 different drawings there. Just giving you a little bit of practice at rotating in both a positive and negative manner, rotating in degrees as well as radians. Okay, then you get to these problems where you're converting. And all you have to know for converting is that you will be using this conversion ratio. Pi is equivalent to 180. These fractions are made out of 2 things that are equivalent, as is always the case when you're converting. It's a matter of knowing when to have the pi at the top and the 180 at the bottom, or should you have it the opposite of that. So basically, the easiest way for me to tell you this is that you have to look at what are you converting into. If they're giving you a number that's already in degrees, you can't possibly be converting into degrees because you're already in degrees. You're converting into radians. Radian is a pi type number. Radians are decimals. Pi is the decimal player in this scenario. That's a degree type number. This is a decimal type number. So whatever you're converting into, you want that symbol at the top when you decide should you use it like this, pi over 180, or should you use it 180 over pi. You always want the one that you're converting into, the symbol that you're converting into should be at the top. So we're going to start off with 105. We're going to put that conversion ratio, which is this thing right here. And we want the pi symbol at the top because it represents radians and we're trying to convert into radians. So pi at the top and what it's equivalent to on the bottom. Okay, what you would have at that point is 105 times pi because this number out front is part of the numerator. 105 is the same thing as 105 over 1. So it's top times top, bottom times bottom. So 105 over 180. And there's a pi symbol at the top. You're going to want to reduce this, and you can bring your calculator in on this account. The degrees are gone because you got degrees on the top, degrees on the bottom, so those symbols cancel. So if you want to get the most simplified version of this, because that's all the homework software is going to accept, reduce it yourself if you want, or put it in your calculator. Just be 105 divided by 180. Okay, and then instead of hitting enter, hit math. The math key is right there in the first column. That key right there, and then hit enter twice. So math, enter, enter. Write that in your notes if you need to. Whoops, I pressed it in wrong, sorry. It was supposed to be 105 divided by, I think I had a multiplication symbol in there, 105 divided by 180. So that's the same thing as the fraction 105 over 180. So again, hit math, enter, enter. And there is the most reduced version of that 105 over 180, which simply plays the role of the coefficient. You still have this pi symbol attached. Okay, so we got 7/12 for the 105 over 180. And then go ahead and attach that pi symbol at the top. That means that you've converted from degrees into radians. Anything that's in pi form or in flat out decimal form is considered to be in radians. Okay, moving to -210. The only difference here is that you're going to have a negative in front of your answer because this is a negative angle. Happens to be in degrees, and you are converting once again into radians. And so, because of that, the radian symbol, which is the pi symbol, should be at the top. So it's -210. Put your little converter fraction right here. You want the pi, the radian symbol at the top, and the 180 that it is equivalent to. The things in this fraction are always equivalent every time you're doing any kind of conversion. Okay, so the degree symbols go away. There's a negative in the answer. You have 210 times pi over 180. And you might want to get your calculator to help you reduce the 210 over 180 as we did in the last problem. 210 divided by 180. And then again, instead of just pressing enter, press math, enter, enter. And you get that reduced fraction of 7/6. So we have a -7/6 pi. Okay, this was your answer here. This is your answer here. Okay, moving on to examples 7, 8, and 9. This one says convert to degrees. Easiest way to do this one. Start off with your 5 pi over 6, and yes, it does have a negative. And you can go like this. You're converting into degrees, therefore you want degree symbol at the top. Look at what you're trying to move into because that is the symbol that should be at the top. So instead of pi over 180, I'm going to use 180 over pi. And in that way, these pi symbols will cancel, leaving you with -5 times 180 divided by 6. And you can pop that right into your calculator. And you get -150. Degree symbol, still part of the problem, which it should be because you were asked to convert into degrees. Okay, moving to example 8. In example 8, same thing. You start off with 3 pi over 4, yet you have been asked to convert into degrees. And therefore the degree symbol in your little converter fraction should be at the top. Okay, here's your little converter. You want degrees at the top because that's what you're trying to convert to, and then what goes in the denominator is what that 180 is equivalent to. Okay, pi symbol cancels, and it's 3 times 180 is what you have left at the top, divided by 4. Okay, so 3 times 180 divided by 4 is 135, and you are in degrees. Okay, moving on to example 10. Oops, I forgot example 9. Don't want to leave that out of there. Okay, so this one is just a straight decimal, and you're being asked to convert to degrees. Again, in each and every one of these examples that I have just done regarding conversion, example 5, 6, 7, 8, and 9, my main point has been to look at what you're converting into and make sure that that goes at the top. In every single one of these 5 problems, conversion problems, I've used a converter fraction, and I've started off with whatever they've given me. So there's what they gave me, multiplied by the converter fraction, and I've made a real point about telling you what to put on top, what to put on bottom. You want degrees on top. The fraction is made out of 2 things that are equivalent, which would be 180 and pi. Okay, what's going to happen in this problem is that you're going to actually press the pi symbol as your divisor. So it's going to be 4.83 times 180 divided by pi, that degree symbol. There's nothing for it to cancel with, so it will remain in your answer. So 4.83 times the 180 that's next to it. You can get the answer for the top if you want, and then divide by second function, pi. Do not approximate for pi and call it 3.14. Actually use the pi symbol, which I called up by just pressing second and then pi. It was my divisor. Now press enter and then round to whatever they ask you to. They'll tell you what place to round to. I'm going to round to the hundredths place here. So I'm going to go 276.74. They'll be really specific about what to round to when you're in whatever software you're using to do the homework. I'll just round to the hundredths place in this case, which was 276.74. Hundredths place is 2 numbers after the decimal, and your units are degrees. You have to have a unit on your answer if one remains. Okay, 5 conversion examples. Let's move on now to the relationship between degrees and minutes. This is the symbol for minutes. Look at the little accent mark. And this is the symbol for seconds. Looks like a little quotation mark. So 1 degree is equivalent to 60 minutes, and 1 minute is equivalent to 60 seconds. Now, you could do these problems by hand, where if they give you, they might ask you, give you something in degrees and ask you to convert it into minutes. The use for this is in the application problems, especially like, let's say, nautical problems where they bring in degrees and minutes and, things that have directions like that. And they could ask you to even go further, to go from degrees all the way to seconds, which would call for 2 conversions in the same problem. I'm going to let you do these on your calculator. I've included the keystrokes that you're going to use doing it on your calculator. Okay, your calculator has a very nice feature for converting from degrees to minutes and minutes to seconds. Okay, so what you're seeing here, and let me just explain this, is something that's in various units. It's got degrees for the units, it's got minutes, and it's also got seconds. Minutes are a portion leading up to the next degree, but you never quite made it there. It is something that is smaller than a degree. In fact, it takes 60 minutes just to make up 1 degree. So this is almost up to 40 degrees. If you would have had another 60 minutes, you would have been fully up to 40 degrees. And then seconds is even a smaller portion of degrees than minutes are. This is smaller than minutes, so this is just some portion. It's a little bit, it's a little bit bigger than 39 degrees, but we want to get it as just 1 continuous decimal. And that's what your calculator is going to do for you. If you were doing these conversions by hand, the same thing. Look at how the directions read. Convert the angle to a decimal in degrees, round to 2 decimal places. So what I am telling you in these instructions that I've given here is how to feed this into your calculator and to attach degree, minutes, and second symbols using your calculator. They are under the key called second angle, and that allows you to attach the degree symbol, the minute symbol. The second symbol is under alpha plus key. And so I'll just demonstrate that. And once you have all of the symbols attached properly to these numbers, the degree symbol attached to this, the minute symbol attached to the 47, and the seconds symbol attached to the 32, then you're just going to press enter to convert and complete the decimal degree form of the angle, just as exactly as it says here. Okay, so here we go. I'm just demonstrating what those words say. Okay, so we want 39. We want to attach a degree symbol, so we're going to go second angle and pick option 1. Then we're going to go 47, again to second angle. Notice that when I press second angle, an angle is just, in the second column, 4 keys down, that this is where you grab the degree symbol as well as the minute symbol. The minute symbol is option 2. So arrow down to option 2, press enter. Now you've pasted a minute symbol to the 47. And then the last thing is 32 seconds. 32. Now this, the symbol for seconds is not under second angle. It's under the alpha plus key. Alpha is this key right here. So press alpha, and then the plus key is right above the enter key. See right there, and you can see that where this plus key is right here, there's your seconds symbol right on top of there. So I'm going to press that. And after you've attached the proper symbols to each one of these numbers, then all you're going to do is what it says here. Once all the symbols are attached, press enter to convert to a complete decimal degree form of the angle. So just press enter, and there you go. All I did is press enter one time after I had pasted the symbols, and this is 39.79 degrees. Once you convert it to a full-on decimal like this, you're in degrees. And I'm going to round it. This says to round to 2 decimal places, so 39.79. Okay, moving to number 11. In problem number 11, you have something that is the opposite of what we just did. It's a full decimal in degrees. We just worked to make that happen in the last problem. Here they're starting you off with that type. So this decimal portion that you're seeing here, it was some amount of minutes and seconds before it was converted to 0.41. See, in the last problem we were given degrees, minutes, and seconds, and we got the calculator to convert the minutes and the seconds to a decimal portion like what you're seeing right here. So we're going back the other way this time. So if you're entering an angle in a calculator that's already in complete decimal degree form like this one, all you have to do is press the decimal into the calculator, then press second angle, and then go down to the option that stands for degrees, minutes, and seconds, DMS, when you're being asked to convert to degrees, minutes, and seconds form. Okay, so really simple, because you're letting the calculator do all the work. So 60.41. Enjoy letting the calculator do all the work, because you're going to be asked to give mostly in this course exact answers. So you're going to have to know how to do a lot of it yourself. Of course, you're going to be using the calculator to help you with any of the arithmetic and reducing and things like that. Okay, so once you have it pressed in like this, then all you're going to do is go second angle, just like that, and go down to the option that says degrees, minutes, and seconds. Okay, you're going to press it once. It knows that you want to do this. Press enter again. And there you go. So I just pressed enter twice. Okay, so this is equal to 60 degrees, 24 minutes, and 36 seconds. Okay, and you'll be using, those functions that I just taught you in examples 10 and 11 to do application problems. And in those application problems, you'll typically have so many other things to do that you don't need to get bogged down just with converting. Okay. Okay, so here we come into some of the application problems where we can use angles to find the length of an arc, and we can also use it to find the area of a sector. I've given you a picture over here to the right of the formula. Right here is a picture. S is the letter that we use for arc length, and this is the formula by which we find arc length. We just take the radius of the circle, so a very nice and easy formula, and we multiply it by the central angle. Any angle whose vertex is at the center of a circle is called a central angle. Okay, vertex at the center of a circle, that's called a central angle. Please pay attention to the fact that, let's see, where can we write this? I'm not going to write it, we're just going to highlight it because it's already been written here for you. The central angle has to be in radians. Do not try to find arc length using this formula unless your theta is in radians. Okay, very important because sometimes they're not going to give it to you in radians. And the answer will not come out right unless it is. Okay, so in example 12, find the arc length. That's just the distance along the rim of the circle, which is cut out by these two radii and also related to the central angle. So here's the formula. Arc length is the radius times theta. You should always write the formula first, especially when you're demonstrating your work for me. And just to help you focus, in this particular problem, the radius is 35 feet. You're required to show your units in your answer. That's part of the points that you get, so don't leave them out. And then we're going to multiply by the angle. It says here that the central angle measures 1/7 of a radian. So they're giving you something that is in radian form. Okay, so this is the R, and this is the theta. And the word radian just means that you have a decimal. 1 divided by 7 is a decimal. So you don't have to, that's not a radian per se, it just means that it's a decimal number, unless they try to force you to talk about radians in the problem. But typically that is not written. So this would be 35 over 1. Remember, it's top times top when one of your multipliers is a fraction. You can think of both of them as fractions. So it's top times top divided by anything that's on the bottom. So just 35 divided by 7 is 5. And that would be 5 feet. And that is the length of an arc when your central angle is 1/7 and your radius is 35 feet. That's exactly what you're finding there. Okay, example 13. Find the length of the arc of a circle whose radius is 50 miles. And then this is, this subtended by the central angle. That just means that the central angle has two sides that created it, that created that angle. Those sides are the radii in the circle. And subtended means that these sides cut into the circle, cutting out that particular arc. So that's just terminology that is used when you have two sides cutting into the rim of the circle and cutting out a particular portion of the rim. And we refer to that as an arc. Okay, notice that this time that the central angle is in degrees and this needs to be in radians. And you can convert it right while you're plugging it into the arc length formula, which is what they're asking you to find. It says find the length S. the arc length S. So this central angle needs to be in radian form. Okay, so here we go. We're going to do arc length. They're asking us for that. That's the radius times the central angle. So radius is in miles, and we're going to be multiplying by theta. And right in this box where I would be putting the theta, I can't put 21. I have to enter it in a way where it's going to convert itself into radians, and I can do this. Okay, this is from the 5 problems where I was teaching you to convert from degrees to radians. Okay, you're starting off with 21 degrees, and you're multiplying it by that converter fraction. Okay, I want to go into radians. Therefore, pi should be at the top, and the 180 that you're multiplying it by, this is the converter fraction that you're multiplying to convert this 21 degrees. The 180 should be down here so that those degree symbols cancel. And all in this shot right in here, you're converting into radians. And we can just enter all of this. So not only are we finding arc length, but right in the midst of finding arc length, we're converting that 21 degrees into the proper form so that it is applicable to this formula. So just think of this, the 50 as 50 over 1. This is top times top times top. There are 3 things that are at the top there. 21 is the same thing as 21 over 1. So all of these numerators need to get multiplied together in your calculator first. Then you begin dividing by any divisors that you may have in the problem. So it's 50 times 21 times pi. So 50 times 21 times second function pi. I like to get my numerator, and the only divisor that I have here is this 180. Divided by 180, and we get 18 point, let's see what we are rounding to, no mention of that. I'll round to the thousandths place. Again, they're going to make mention in each problem of what they want you to round to. I'm going to round to the thousandths place. Okay, so mine is 18 point, and from what I got here, thousandths place would be 0.326. Only unit that I have that has not gone away is miles. Degrees is gone. Okay, area of a sector. So the area of a sector of a circle is given by the following formula. Now, area, unlike arc length is related to the circumference of a circle. You're just taking out a portion of the entire circumference, whereas area is all of this. Okay, so the formula that we use to find all of that area is 1/2 r squared theta. Yes, again, we're going to be using radius. And again, just like in the arc length formula, central angle has to be in radians. Okay, must be in radians for either one of these formulas. Okay, so it says find the area of a sector of a circle with a radius of 40 and a central angle of 1/5 radian. So this is perfect the way it is. So I'm going to do my formula right down here. It's 1/2 times r squared times theta. I'm going to plug in 0.5 for 1/2. For my r squared, it's going to be 1/5 of a radian, and you don't really need to put radian because that just means that you have a decimal. 1 divided by 5 is 0.2. Let me make this a little bit closer. So we did the r squared. Whoops, I didn't. Oh, I did that wrong. Okay, so no. My mistake. Let me fix this. The radius was right here. That's what I should have been squaring. So r squared should have been 40 squared. I put that 1/5 in too soon. And it was in miles. You're going to want to put the units in there too, because again, units are part of the answer. You get points for those. And I want to know that you understand that area always has units squared rather than to the first degree. Okay, so it's 0.5. That's this 1/2 right here. Then it was the radius squared. My radius was 40 miles squared, and then multiplied by theta. That central angle theta has to be in radians, and it is. There, now I have everything in the right place, and you can go ahead and press that in. Only divisor that you have here is the 5. Everything else is considered a numerator. So it's 0.5 times 40 squared times 1. You don't need to press in the 1. So 0.5 times 40. And you can put a little square on there by just pressing the x squared key. So I just put the 40 and then tap that key. You can get that numerator value and then divide it by 5. And it turns out to be 160 given by my calculator. And then the units would be right here, miles squared. And there's your final answer there. This was the final answer for this. And this was the final answer for this. And that was the final answer at the top. Okay, taking us to the next page, example 15. I'm going to make this the examples in this section on angles and their measures in a two-part video display. So I'm going to go up through number 16, and then I will do the rest of the examples in the second video for this section. Okay, here's example 15. Find the central angle theta, which forms a sector of area 27. So right there, they're trying to point out to you what formula to use. Forms a sector of area 27 square centimeters. So if they're talking about area of a sector, then you should be taking out that formula that we just used, which was 1/2 times r squared times the central angle theta. Okay, you can press this in as the 1/2, just easier. Let's see, and the question here, we already know the radius. The radius is 8 centimeters. This formula says that you should be squaring your radius. That's my radius, there it is squared. The theta is unknown. In fact, that is the question, so we don't have anything to plug in for it. We're actually solving for it. And this time we do have the area, 27 square centimeters. 27 square centimeters. Okay, so now what you're going to want to do is start isolating this theta. Get a single number here first. It'll be the coefficient of theta, and then we'll divide both sides by that single number. So it's 0.5 times 8 squared, which should be 32. Okay, so we have 32. That's 0.5 times 8 squared. So this side now says 32 theta. Over here we have, and let's not leave the units off. Let's see where I can put that. I should put it right next to what it belongs. I'll wedge it right in here. So 32 centimeters squared times theta, and then over here we just have 27 centimeters squared. Okay, I want to divide off this coefficient of theta so that I can solve for the central angle theta. Okay, so 27 divided by 32, and we get 0.84375. And they said that we could give this answer in radians, and therefore this decimal is good. Any kind of decimal number, whether it's a pi type number or a flat out decimal, is considered radians. Now this says type an integer or decimal rounded to 3 decimal places. So our answer that we're going to give is 0.844. Okay, example 16. Find the arc length and the area. Okay, so arc length, we have this formula. Remember, for both of those, whether you're finding arc length S or area A, you need your theta to be in radians. So you're going to have to convert this theta. This is your central angle. It's just not in the right form. You need this to be in radians. But you can convert it right in the midst of doing the particular formula that you're going to be using for arc length and area. And I'll demonstrate that each time. Just don't forget that it's your angle, your central angle is not usable while it's in degrees in any of the formulas you're going to be learning. Okay, so here's my formula for arc length. Okay, so it's going to be the radius, 12 yards. And then I'm multiplying by the central angle, but it has to be in radians. Right now it's in degrees, and I want to convert it right out of degrees. So I'm going to multiply it by this converter fraction that will take it out of degrees and into radians and pop all of that in the calculator. So not only am I converting the 80 degrees, but I'm also finding arc length all in one shot. Okay, so again, you only have one divisor here, and that's the 180. The degree symbols cancel with each other, so the only unit that you're going to have left in the end is yards. You're going to go 12 times 80 times pi, get that numerator, and then divide by 180. 12 times 80 times second function pi, get that big number, divide it by 180. And you get 16 point, let's see, are we asked to round to anything? 3 decimal places here, so 16.755. 5, and we are in yards. That's the arc length. Okay, you've also been asked to find area of a sector. Okay, so area of a sector, formula for that is 1/2 r squared times theta, again must be in radians. So I'm going to use 0.5 for my 1/2. My r squared is that 12 that you're seeing there. So that 12 is going to get squared as well as the units that are with it. And then my theta, that theta converted into radians. And you saw how I did that. Let me demonstrate that again because I have to do it in this problem as well. This, you're starting off with that 80 degrees, but getting it out of degrees just by multiplying by this converter fraction. The 180 on the bottom, where the degrees will cancel, bringing it into a pi type number since the pi unit is at the top. When you enter this in your calculator, you can just enter it as 0.5 times 12 squared times 80 times pi. All of that is part of the numerator. Only divisor are the numbers underneath the fraction bar. So this would be 0.5 times 12 squared times 80 times pi. Call it that pi value. There's my numerator divided by 180. And you get 100 point, again, I think it's rounded to 3 decimal places, 100.531. 100.531. 1, and since this is area, it's yards squared. Okay, that's going to finish the first video for me, and I will complete the rest of the problems in this section in the second video.